Let's talk about the edge bundling. Basically, we have a bunch of edge and we wanted to bundle them together like this and create some kind of interesting structure. So let's see. First, I put on a curve, resample it, and copy some geometry on it for the top and the bottom and scatter some points. And I use the point wrangle to add a polyline randomly between these points. But actually, I don't want to bundle the diagonal line because even you can bundle them together, it looks terrible. So I use an wrangle to determine the angle between the up vector using the dot product, and just remove some of the polylines. Yeah, and then we are going to use the algorithm design in this paper. It's called the let's find it. This paper is called the FDEB, the Force-Directed Edge Bundling for Graph Visualization. And what it does is for each line, it will subdivide it into multiple points. And for a pair of lines, we will apply a spring force inside the line, and another force, some kind of like an electronic force, which will attract the positron to the electron, so they will be attracted to each other. So you can see the formula here. This is the spring force, basically the pi, and defined as a distance between a point before it and the point next to it. And also the electronic force. For each pi, we calculate the sum of the forces with all the other pair of q. So for p2, we calculate the forces, the force between p2 and q2, p2 and q1, p2 and q3, and is divided by the square of the distance. So basically, the inverse, kind of like a inverse distance law. But in the actual code implementation, we could ignore actually the forces between P2 and Q1, P2 and Q0. We only calculate the forces between P2 and Q2 because these the forces between other particles is very negligible. They are quite small, so we can ignore them. And if you just calculate the forces between P2 and Q2, or even if you add the forces between other points, the result will be quite the same. So for faster calculation, we just calculate the forces between P2 and Q2. Okay. But obviously we don't want it to wait a second. Obviously we don't want it to calculate the forces. For example, for this line, we don't want it to bundle it with every other line. We wanted to make sure somehow we wanted to set some condition, so it only bundle with some lines that is close to it and has some, maybe the angle is quite the same and the length of the line is quite the same. So there is a compatibility check designed by the paper author, which is depicted in this section. The author has designed 4 compatibility check. The angle compatibility basically is calculate the angle between 2 lines by using the dot product. And the scale compatibility is basically the length, and by smartly design this function, which will output between 0 and 1, it basically measures how close the length of these 2 lines. And there are other 2 kinds of compatibility called the position compatibility, and you can read it in the paper. And the visibility compatibility, basically we will project the start point of Q0 and Q1 to the original line P to get the I0 and I1, and we will calculate the function which is designed here, which measures the compatibility, also output a real value between 0 and 1. So after all the calculation, we multiply all the compatibility together and use this as a threshold to define maybe this line is only compatible with some of the lines it compatibles with. So we store we use the compatibility. Let's see the code here. Basically, we just loop through every one of the primitives, and we don't want to measure the compatibility with ourselves. We measure with other points, so we sample all the points with other primitive, the line, so we call print points and get all the points on the other line, and then the start point, end point, and we just calculate the other line's distance, the length and direction, whatever, and then just use the math inside the paper to calculate the angle compatibility, the scale, the position, and the visibility compatibility, and then just multiply them together, and then you just set a threshold to remove, to only we add all the primitives that is compatible with the current primitive to an array. So we store it in an array. Yeah. So we can, in the solver, for each of the primitive, we look for all the compatible lines with us and apply the forces and bundle them together. Oops, I forgot to turn back my Houdini. Yeah, that's it. So yeah, in the solver, we basically, when we calculate the compatibility test, we store all the primitives that's compatible with us within this array. And I wanted to talk about one of the smart formula inside the paper, which we could learn something. That is the scale compatibility, given we wanted to measure how close these given two lines, how close their lengths are. By using this function, which will output a value between 0 and 1, it's very useful. And we can visualize it inside the Houdini, like basically I just put down the grid, and then that's the formula. And for the x-axis, wait a second. Yeah, it should look like this. For the x-axis, it's the length of one line, and for the z-axis, it's the length of another line. And if they are equal, we output the value 1. And if that difference very much, we output 0. So I think this function is quite smart to measure the closeness of the length between two lines. Yeah, maybe. And yeah, and then in the solver, we basically just apply the forces between, nothing special, just loop through for a primitive sub, and then loop with all the other compatible primitives and apply the the forces defined in the paper. And then actually there's no need to smooth. Yeah, and then run the solver. Yeah, and that's basically it. And we also have a curve view attribute from 0 to 1 for each line, so we can use it to remap the thickness and put it into the polywire to define the thickness of the curve. So we could have some kind of this structure. There's one problem here. If we are actually trying to divide, creating some kind of like a tube, by using this algorithm, using the sub-solver, we are colliding with ourselves. I think one of the solution might be to use the Valen. We could use the Valen string and then set because string has a thickness attribute which is stored in the p scale. We could see it here, 0.09 the thickness, and we override the thickness by our own we override the p scale by our definition of the thickness, and then we can pump it into the volume solver to untangle this line, overlapping lines, to resolve the self-collision. And I also use a pop interact to kind of like for each of the line there is an electron inside it, so they will repel each other. But I still not quite be satisfied with this result, but I think it is worth a try, or maybe tweaking some parameters will give a better result. So let's see what the vellum how the vellum resolve our problem. Wait a second, I don't know why my vellum just wanted to calculate to the 15th frame, but I'm still at frame 3. Holy. Alright, you can see that we are trying to I have turned on the visualizer and turned on the thickness. You can see that we override the thickness here. If we have not overridden, all the thickness will be uniformly. I really hate the vellum solver why it keeps calculating. Alright, let's see. It's try to detangle itself, and then I just smooth it a little bit by using the vellum post process. So we got this. This is before and after. But actually, it's very hard to completely detangle the self-collision, because they are basically just overlapping each other. So I think the problem is we should solve this problem just inside the vellum instead of inside the subsolver. But you should put it into the vellum only if you try to design this kind of tube structures. And if we think of it like some creature structure, or maybe we are even going to use VDB polygon to merge them together, and I think it's fine to just use this algorithm to output the line and then to decide what to do. So let's try the VDB polygon. Yeah, maybe we could turn it back, VDB convert. Convert it back to the polygon. Stop. We should increase the resolution a little bit. What is it calculating behind? That's so strange. 0.03. Yeah, this give us a better result, like this.